In this video, we will derive the expression for Einstein mass-energy relationship. As we know that in the theory of relativity, mass is not absolute quantity. For example, if we have any particle, if we displace that particle through displacement dx on application of the force F, so this we have to do work, and that work we can write this as a dw is equal to F dot dx. And you know that this work done is appear in the form of the kinetic energy of the particle, because on application the state of the particle will get changed. So this we can write is change in the kinetic energy ek by this symbol F dot dx. And we know that according to the Newton's law, Newton's second law, the force is given by the rate of change of momentum, like this. So we can write this force m into dv dt plus v into dm by dt. Say this is expression 1 and this is expression number 2. So when we can substitute this, we substitute this expression of force in this equation 1. So this dek comes out to be m dv by dt plus v dm dt into dx, or I will rearrange it like this: m into dx dt dv, I will do this, plus v into dx dt into dm. Here I will replace this dx dt with the velocity. So this above relation of change in the kinetic energy comes out to be m into v into dv plus v square dm. So this is equation number 3. So this is the change in the kinetic energy, or expression in the relativistic physics. So we know that in non-relativistic physics, the expression for kinetic energy, we know that this is half m v square, and this is the expression in the relativistic physics. And we know that the mass is not absolute quantity in the theory of relativity. So the expression for mass is m by m naught into 1 minus v square by c square, where this m naught is, we call it rest mass of the particle. And this is the variation, m represents the variation of mass with velocity. So by using this expression, on rearranging this m into 1 minus v square by c square is equal to m naught, can write this m squaring both sides On squaring both sides, we can write this m square c square minus m square v square m naught square c square. So on differentiating this expression, it on differentiating, I will write it as 2m c square is constant into dm minus 2m v square into dm, and now differentiating with this with b 2m square v into dv. Here m naught is rest mass and c both are constant, and differentiation comes out to 0. Now I will rearrange this expression. On rearranging this, because in this expression 2m is common, so I can add this c square dm is equal to v square dm plus v into m v into dv. So select this expression is at 4. Now on comparing, equation 3 with equation 4. So on comparing, we know that this side, both side, right hand side of equation 3 and 4 are same, so I can write dek is equal to c square dm. So now in order to find the expression for kinetic energy, total kinetic energy ek, we can differentiate it, not integrate it, from when the mass changes from or kinetic energy changes from 0 to ek, and mass changes from m naught to m c square dm. So this is, write this ek and c square is constant into m naught to m into dm. It comes out to be c square into m minus m naught. So this is the expression for kinetic energy, or you can say this is the relativistic kinetic energy of a particle. And the total energy of a particle is equal to, comes out to be rest mass energy plus relativity kinetic energy. This is m naught c square plus m c square minus m naught c square. So it comes out to be, I will denote it with symbol capital E. This m naught c square, m square get cancelled, and we will get here E is equal to mc square. So this is very well known expression, we will call it Einstein. mass energy relationship. Or mass energy relation. Now now we will drive the expression of kinetic energy at low velocities. That kinetic energy at low velocity. We know that the expression for relativistic kinetic energy was mc square minus m naught c square, and we know that m is equal to m naught 1 minus v square by c square. We substitute the value of m naught m here, it comes out to m c square 1 minus v square by c square minus m naught c square. So by using binomial theorem, m naught c square 1 minus v square c square minus half m naught c square. So this expression at 1 plus v square by c square 2 minus m naught c square, because we will neglect here, in this case we are considering v is very less than c, velocity of light, so we will neglect here higher order term, we will consider only this up to this term. So it comes out to be m naught c square plus half m naught v square minus m naught c square, and this is equal to half m naught v square. So this is the expression of the kinetic energy in case of non-relativistic physics. So at low velocities, the expression or the kinetic energy is same. And another is, if we plot the kinetic energy expression, kinetic energy along this axis, and here vy c in this direction, so it is 0.1, 0.3, 0.6, 0.9, 1.1, or here it is say 1.4, like this. So the if we plot this non-relativistic kinetic energy expression, this is half m v square, so it will, as the velocity is increasing, it just will go on increasing. What in the case of relativistic, because here v is equal to c is equal to 1 here, if we plot this relativistic expression of kinetic energy, this, so at low velocity they are same, but as we approaches the velocity of light, so this represent m c square minus m naught c square expression. So this is the, you can say, the classical comparison between there is a comparison between this is classical and this is relativistic formulas of kinetic energies. So the variation is different in both cases. So this is regarding the relativistic kinetic energy.